All right, hello class, and welcome back to part B of lecture 2. In part A of this lecture, we sort of went as far as we could with the n-body problem. And in this lecture, therefore, we're going to restrict ourselves to the two-body problem. That is one object in orbit around another. To get there, however, we have to tidy up a few things. So we're going to take that n-body problem and try and simplify the dynamics substantially. To do so requires a certain set of, not simplifications per se, but reductions, I guess you could say. And so, of course, the first thing, which we already discussed in part A, was to consider relative motion. So that is, we consider the distance from object 1 to object 2. Okay. So we don't consider the absolute position of the body 1 or body 2 in this coordinate system. Well, that's okay, and in fact this is more or less the problem that we'd like to solve. However, we can reduce this problem somewhat, or at least make it a little bit more tractable by, or interpretable I should say, by considering conversions back and forth from R1, from the relative position to absolute position. So to do that, the first step we're going to take is to redefine a coordinate system, or define a coordinate system, since we haven't actually defined one yet. And so we're going to define a coordinate system where we place the center of the coordinate system, or the origin of the coordinate system, at the center of mass of those two bodies, right? We know what the center of mass of n bodies is, and of course that reduces to something even simpler for two bodies. So the center of mass is the weighted average of the position vectors in this sort of absolute coordinate frame to the masses themselves. And so our first simplification is going to assume that the absolute position of the center of mass in our coordinate system is 0. Right? So the origin occurs at this what's called barycenter if we have two bodies orbiting each other. And so this is the origin of our coordinate system. So if we do that, it simplifies things a little bit in that we can solve this equation of motion, right, R1, 2, and then in the case of a planet in a spacecraft, for example, that will be almost identically equal to the position of the spacecraft relative to the planet. However, we don't need to make that assumption quite yet. That's called the restricted two-body problem. We don't have to make that quite yet. In fact, even if the masses are comparable, so say the moon and the Earth, for example, or two binary stars is another good example, orbiting each other. That's not a good orbit, though. You could say and something like that. Right. So we can solve this equation, and that's the solution to that is given by Kepler's elliptic motions. So we'll talk about that more in the next lecture. So if we solve this equation, which we can, even for comparably sized, in the absence of a restricted two-body problem, if we solve this equation, get the elliptic motion, right? Well, that's going to tell us the position vector. It's going to allow us to solve for R1, 2 as a function of time. So we're going to solve that, and we'll be able to determine R1, 2 as a function of time. Right. Of course, that in this sort of comparable mass situation, the Earth Moon, or say the binary star problem, that may not actually tell us the information we want to know. However, it's not going to give us these motions, right? Which is actually what we want in this case, R1 and R2. Fortunately, however, we can reduce, or we can solve for those two motions as a function of time, given R1, R2, right, as a function of time. And how do we do that? So that's what we're sort of looking at on this slide and its notes. So to do that, we first note that here, right, we have this relationship. Actually, I should box it a little bit larger. We have this relationship which allows us to express R1 as a function of R2. So for example, we can solve this equation to get R1 equals negative R2, and where we have an M1 here and an M2 here, but we can, let's say, divide through by M1, and so we can express the absolute position of body 1 as a function of the absolute position of body 2. Well, how does that help us? Well, remember that R12 is R2 minus R1. And so if we have a solution to R12, right, if we solve for the position of R12, then by plugging in this equation here, right, for R1, we can see equals R2 minus cancels out, R2 M2 over M1, and then we can pull out the factor R1, R2 there, and we get M1 plus M2 over M1, right? So we can solve for R12 as a function of R2. Of course, that's not what we want. We want the other direction. So we just divide by this factor here, and we get the expression for R2 then as a function of R12. So if we solve this, this set of dynamics for elliptic motion, then we can use that to reconstruct the positions of the individual planets, or stars as the case may be, using these formula, right? So if we, let's see, where can I erase something here? So again, right, if we go back to that picture, right, here, where we got, here, I'll just move the coordinate system over here so these things aren't all in a line, right? R1, R2, and remember, this vector is R12. Remember, it's the position vector of R2 minus the position vector of R1. So it's the position of R2 relative to R1, or relative to the first mass. Right. So using that, we can then deduce the absolute position of R2 and R1. Right. So that's useful. And of course, in the restricted two-body problem, we take this a little bit further, right? We make this the additional simplification where we assume that the mass, say, of mass 1 is very large and the mass of mass 2 is relatively small. And so in that case, when we look at these coefficients here, this one and this one, that is, right? Well, then we've got if M1 is big, very big, and M2 is very small, then we're dividing something small divided by something big. And so this whole term becomes approximately 0. That is, the planet doesn't move substantially, even though we have this function R12, which may be large, but the motion of the planet caused by the spacecraft is relatively small. Conversely, if we look at this factor over here, well, M1 plus M2, M2 is very small, so we can essentially ignore the M2 there, and then we have M1 divided by M1, and so actually the motion of the spacecraft in that framework is just the solution to that to this equation, the elliptic motion, as measured from the barycenter, of course, but then in this case the barycenter will be very close to the planet, the center of the planet itself. Right? So in the restricted two-body problem, we have this assumption, or this sort of that's a restriction we make in the two-body problem. If we want, we can actually solve directly for ignoring, we can cut out the middleman, if you will, the R12, and solve directly for the position of that spacecraft, or the position of the moon, if you will, by a series of simplifications. And there are no simplifications here, right? These are just reductions, substituting in vectors. So if we look at the acceleration of R12 double dot, well, remember, R2 vector is m1 over m1 plus m2 R12. And so the acceleration of that, right, we just move the double derivative there to the right. And then we plug in our expression for R12 here, right? This is just that. And then we see, well, that term cancels out that term. And so we have an expression now for R double dot in terms of this position vector R12. But of course, that's not what we want. We want to express R2 double dot in terms of R2, right? Actually, sorry. Here I've made a couple mistakes. Actually, these should be 2's here because I updated my notes. My apologies for that. Those should all be 2's. Right, there we go. So we take this expression, of course, and then we know what that is, right? Because we just invert this relationship, R12 equals m1 plus m2 over m1 R2. And so we plug that expression into here, and then we get that m1 plus m2 over m1. Here the m1's cancel out again, and we just get this expression for R2 double dot in terms of R2 itself. Now, we are, in fact, of course, still dividing here by R12 cubed, however. And so we have to do that substitution again. So we again substitute in here. And now that this coefficient here gets cubed, right? The cube of that and the cube of that and the cube of that. And so we get this, this cubic expression appearing here. So let's see, where is that? So the cubic expression pops up there. And now what do we do? Well, we have this cube here term. Let's see, this term cancels out the cube, and that makes it squared. And then so we got gm cubed over m1 plus m2 squared. Right. Well, okay, so now what are we going to do? So first of all, we look at that expression, and we now can make an approximation here. Now, this is the point where we make an approximation if we like. We don't have to, of course. We can keep this. We can keep this term here. Right. This is if we want to solve directly for the motion of R2. Right. We can not make the mu assumption. We can keep this as our new mu modified and solve the elliptic orbit problem using that modified mu. And that will actually give us directly the position of the spacecraft without worrying about, or the moon, if you will, without worrying about the position of the planet. Okay. However, of course, in the restricted two-body problem, we do make that assumption. M1 is significantly greater than M2. And so in that case, M1 plus M2, when we square that, that's going to be very close to just M1 squared. And so that m1 squared cancels the exponent there, and we just get gm1, which is in the restricted two-body known as our gravitational parameter. We use that expression, of course, because it only depends on the mass of the planet and not the mass of the spacecraft or mass of the moon or whatever. However, you can keep in mind, though, that if you actually wanted to solve this problem for the case where this assumption doesn't hold, you can just solve the initial the elliptic orbit problem using this modified value of mu, this modified coefficient, because it's just a constant. So when m2 here is not trivial, you can just add a little term to it, and you get your new mu. Right. So that sort of disposes of, so first, in the first part of this lecture, of course, part A, we disposed of the n-body problem. And now we've sort of disposed of the two-body problem, where the masses are not imbalanced, so that where the masses are not, don't satisfy this inequality. And now we've come to the point, of course, where we'll take the rest of the course, which is the restricted two-body problem. So now we'll talk about the restricted two-body problem. And that, just the restricted part just means we make this assumption here, that the mass of the planet, in this case, is significantly greater than the mass of the spacecraft. Right? And so when that's true, right, we can just cross this m1 out of the factor, out of the dynamics, and the dynamics are given solely in terms of this constant mu, which depends solely on the mass of the planet, and of course the gravitational constant of the universe. And so in the case where the things that we're considering of relatively low mass, we don't need to consider that mass. We don't need to consider that mass in coming up with our equations. And so when we're considering spacecraft, for example, we don't consider the motion of large spacecrafts any differently than we consider the motion of micro spacecrafts or microsatellites or picosatellites or anything small. Small and big at this stage of the game doesn't make much of a difference. Of course, if you have a moon-size spacecraft, you put a thruster on the moon, for example, okay, then you've got to use that coefficient from the previous slide. But even then, right, you can still use the coefficient from the previous slide, and all the dynamics work out. You just have to modify your mu a little bit. And so this mu is actually the parameter that we'll be focusing on most in this course, right, which is it depends on the planet, of course, because it depends on the mass of the planet. But these are all well known for all of the things that we're going to be orbiting. So, for example, the Sun has a known mu, which is rather large, 10 to the 11th. But it's known, and this is the parameter that we'll be interested in. We're never really interested in the mass of the Sun per se, or the gravitational parameter of the universe per se. We're almost always interested in mu because that's what determines the motion of the Sun. It's only when the orbiting object has a mass which is a significant fraction of the thing it's orbiting that we have to make a correction to that. And even then, we still just use a modified value of mu. So we never directly look at that factor of the constant of the universe or the mass of the planet itself. So I list here some very important mu's. Mu of the Sun is hard to remember, so I don't expect you to remember on all exams. I'll put that into the header of the exam, so you'll just have that constant with you. I'll do that with all these constants, really, but the two constants you should, because we consider Earth satellites much more frequently than we consider other things. The two constants which you should try and remember are, first of all, the mu of the Earth, which is 398600. It's easier to remember without the exponent, I think, and it also sounds kind of 398600. 398. It's easier than a telephone number. I can remember 398600. The other, of course, number that you need to remember, and we'll come back to that a few times, is the radius of the Earth, which is 6378. Radius of the Earth, 6378 kilometers, 6,378 kilometers. Why do we know that? Why do we care about that so much? Well, a couple things. First of all, that tells us how much potential energy we have at the surface of the Earth. Remember, potential energy is mu. Actually, I haven't said that, but we'll talk about it soon. Mu over r, right? We had a different calculation on the previous, when we talked about the n-body problem. But in the two-body problem, the potential energy is just mu over r, or negative mu over r, because potential energy is negative. And so on the surface of the Earth, you already have some potential energy, which is given by this value 6378. So a very important number there. The moon, we don't talk about the moon too much in this class, but it has its own gravitational parameter, which is relatively small, right, 10 to the third. Its radius is a little bit smaller, 1378, or no, sorry, that's very confusing. 1738, it's very close to like the Earth, but it's like the The 7 and the 3 are swapped, right? 1, 7, 3, 8. So anyway, the important point, of course, is that each body that we're orbiting has its own mu, which is, of course, changes the size of the orbit and so forth. But it doesn't change the shape of the orbit, right? The shape of the orbit doesn't change. It's only that factor of mu which influences the size of it, and some other things. We'll talk about that in more detail. Right. So what else? What else can we say about this mu? How is it calculated? Right? How do we know this mu? Well, honestly, we know this mu from Kepler's third law, and we'll talk about that in a bit. Where actually we have, I believe it was t squared over a cubed equals, I believe it's mu over 4 pi squared. So in fact, actually, you can calculate this mu relatively easy, and people could do this from just the time of Newton, actually from the time of Kepler, but of course they didn't have mu, but mu came from Newton. Newton could immediately figure out what mu is just by looking at the period of a particular planet and its semi-major axis, which are relatively easy to measure. And then you could just figure out what the mu is. So mu is easy to measure. Mu is known very quickly. However, going from mu to G and M is much harder, right? So measuring the mass of the Earth, very difficult. There's no scales, right, where you can just like weigh the Earth, right? It's very big. And of course, no one knew what the gravitational constant of the universe was, right? So if you knew either of those things, you could figure out what the other was. So if you knew, it's easy to find mu, and if we could weigh the Earth, or find the mass of the Earth, we could figure out the gravitational constant, or if we could figure out the gravitational constant, we could figure out the mass of the Earth. Unfortunately, both of those things are hard to figure out, and it wasn't until, I believe, after Newton died, that the gravitational constant of the universe was actually measured with any accuracy. A brief digression back to the full two-body problem, where we from the previous slide. So if we actually look at the Earth-Moon orbit, so the orbit of the Moon around the Earth, we can actually figure out where that barycenter is. So if we go back to that, those calculations over here, so we can actually figure out how much the Earth moves due to the motion of the Moon by looking at this factor here. This is the mass of the Moon. This is the mass of the Moon. This is the mass of the Earth, and this is the separation between the Moon and the Earth. Because the Moon is in almost a circular orbit, not quite, but almost. Actually, the elliptic motion of the Moon around the Earth is what there are certain tides which actually are affected by the distance from the Earth to the Moon. But anyway, back to that slide over here. So we can figure out approximately the motion of the Earth, or the magnitude of the motion of the Earth, by looking at that constant. And actually, it turns out it's non-trivial, right? So we just take these numbers from the previous slide. The mass of the Moon was, I think it's up here. Mass of the Moon was 10 to the 22, right? 7 times 10 to the 22 approximately. Mass of the Earth is 6 times 10 to the 24th approximately. And the distance between them is approximately 384,400. So 384,000 kilometers. So you just plug those numbers in, and we find that actually the barycenter of the Earth-Moon system is 4,652 kilometers distant from the center of the Earth. So actually, in the Earth-Moon system, right, there's this point below the surface of the Earth, and it is below the surface of the Earth, because remember, that's less than 6,378. There is this point below the surface of the Earth about which the Earth is rotating along with the Moon. So the Moon goes that way, and the center of the Earth actually rotates about that barycenter. can like visualize that here with this nice GIF I pulled off Wikipedia. So this is the Earth. There's the barycenter of the Earth-Moon system, and you can see that they're both rotating about that barycenter. So that's an interesting point. It doesn't actually change very much because remember the motion of the Moon about the Earth is relatively slow. So that centripetal acceleration, if you will, caused by motion about this barycenter actually doesn't change the tides significantly or anything like that. It's actually the gravity of the Moon that changes the tide, that causes the tides, and not and Moon and the Sun, I should say, that causes the tides, and not that motion that you're seeing here. Right. So back to the gravitational constant of the universe. As I mentioned, it's hard to calculate, but you do actually need it in the non-restricted two-body problem, right? You do need it because, right, those masses are roughly comparable, so you need to actually factor this in. Remember, if we go back to this this approximation here, right, we need to figure out what this term is, this term right here. And so that requires us to figure out what are the masses of the Moon, for example, and the Earth, and that gravitational constant, because it changes the elliptic motion slightly, makes it smaller. So how does one figure that out? Well, as I mentioned, it wasn't actually calculated until significantly after Newton's death. And you might think, right, this is the time, it's after 1776, so America was a thing at that point. But it wasn't a full thing, because I think actually around 1786 we had the Constitutional Convention going on, right? So there's Articles of Confederation. So this is a long time ago. I mean, Ben Franklin's out there flying kites in thunderstorms and stuff like that. So a non-trivial quest, and people were interested in this question. They would like to calculate the mass of the Earth because it's saying, hey, I would like to, it's a cool thing to know, right? How much does the planets weigh? And it tells you something about the planets too, right? The composition. Newton actually guessed. Newton guessed the constant actually pretty well. Newton guessed the constant pretty well. He guessed, I believe it was 7 times 10 to the negative 11th. And he did that by assuming that the density of the Earth was 4 times that of water. Density is 4 times the density of water, so the density of Earth. So it makes sense, right? I mean, there's a lot of rock in the Earth, and like rock is about 4 times like maybe heavier than water in general. So that was just his guess. It turned out it was remarkably accurate, although there was no way Newton could have known that. I don't know what he based his guess on, but the actual value is like 6.67, right? 10 to the negative 11th. So hey, wow, that was pretty good. But in any case, no one knew if Newton's guess was correct. I mean, honestly, you could it was Newton, so Newton's guess is you can take that over other men's facts, right? By the way, that's a crib from, I believe it was Star Trek 4, the one with the whales, where Spock is like calculating something, and he tells Kirk he has to make an educated guess on this parameter, and Kirk says, "I would take your educated guess, Mr. Spock, over most men's facts." Well, I would take you could probably take Newton's educated guess to the bank over most men's facts at the time, certainly. And in fact, actually, we'll see the first measurement of the gravitational constant of the universe was relatively inaccurate. Anyway, it was a major scientific quest. Lots of people worked on it. And how does one find that? Well, I mean, right, obviously, to find it, you've got to measure, right? I mean, you just look at Newton's universal law of gravitation, G m1 m2 over r squared, right? And well, how do you figure out G, right? Well, you take 2 masses of known mass, you put them a distance r from each other, right? Mass 1, mass 2, here's r, and you measure the force exerted on them, right? You measure the force, you know r, you know m1 and m2, and so you can just figure out what G is by dividing force by the mass and multiplying by the square of the distance. Unfortunately, of course, we know that we're not magically attracted to each other because, right? Well, okay, maybe we are, but not due to gravity. The gravitational force between reasonably sized objects is almost trivial, right? So how are we going to measure this, right? Because we can't just like put a spring, attach a spring to the wall, and here's me. Right, here's you, you're in cement or something like that, and measure my attraction. Can't do that because it's almost zero. There's no spring which is accurate enough to measure that force. So how was it done? Right. So the first accurate measure, sorry, I said 1768, it was actually 1798, so a little bit off there. So the first accurate measurement of the gravitational constant of the universe was made by Cavendish through what's called a torsion balance apparatus. And incidentally, torsion balance apparati are still the most accurate means of measuring the gravitational constant of the universe, as we'll show in the next slide. So how does this work? Right. So it's really quite clever. So here we go. Here's the apparatus. Right. You take a ball. M1. You take another ball. Well, so we have like two sets: to A, double the force, and B, to just make things balance out better. So you take these two other masses, M2, and okay, the gravitational attraction on mass 1 due to mass 2 is almost trivial, right? So how are we going to possibly measure it? Well, the answer was to create essentially a very, very, very sensitive spring. So what was done was it takes a single quartz fiber, you hang it from the ceiling, right, and you attach it to this bar here. And so what does that do? Well, first of all, quartz fibers have very low torsional spring constants, so they'll resist that torsion very weakly. Right. So very small torques on this quartz fiber are going to cause very large angular deformations. Second, the mass is on a bar, which means that the force, the torque produced, the force amplifies the torque by the length of the bar, right? Torque equals force times distance. And so the longer the bar, the more amplification of that force. And so that's the name of the game, amplifying that force to produce a larger and larger torque. Right. So by extending this out onto a bar, you're amplifying this force, producing a larger torque, which is very difficult to resist by the quartz fiber. And in fact, actually measuring the spring constant or the torsion constant of the quartz fiber is itself very difficult to do, because the only thing, right, that is measurable is gravity, right? Anyway, so we'll come back to that in a second. So then how do we measure first the deflection or the rotation, theta, of the quartz fiber? Well, that was done by attaching a mirror to the quartz fiber. And so what that allows us to do is amplify the rotation. So the mirror rotates with the quartz fiber around an angle theta, which is undetectable. It's impossible to observe, except that if you shine a laser, and obviously there were no lasers, it's just a light source back then, but a point light source, let's say, a very sort of parallel-ish light source, you measure the reflection of that light source, and the deflection, right, that laser, if we think about it that way, right, the motion of where that laser hits this scale over here is going to be equal to, right, d equals theta times r. Or actually, I'm using d too many times, so let's call it x, delta x. So the change in where that laser hits, delta x, is proportional to theta, yes, but amplified by the distance at which you measure. So you can put this scale way over here at a really large distance and amplifies this measurement substantially. And so then you calculate theta as delta x over r, right? And so this allows you to measure very, 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 very small changes in deflection. So again, lots of amplifications going on here, right? Amplifying the torque, the force by the moment arm, amplifying the angular deflection by this very long, it's not a moment arm, but very long amplification factor through the distance. Okay. Of course, that's not the entirety of the problem. Then there's the problem of measuring the spring constant of the fiber. That was actually done by observing the frequency of rotation of this this mass about its equilibrium point. So that the frequency of the rotation, right? If you remember, if your pendulum, right? A pendulum its frequency is proportional to the length and to gravity. So you can actually figure out what that restoring force was. Right? So using all of these measurements, Cavendish came up with a relatively accurate first principles experimental-based method for measuring the gravitational constant in the universe, which he measured as 6.754, which is a little bit high, not too bad. It's off by say 0.1, less than 0.1. It's less. The error is less than 0.1. Times 10 to the negative 11th, I should say. Of course, nowadays we can measure it slightly more accurately, but surprisingly, actually, we can't measure it that much more accurately. And in fact, people keep measuring the gravitational constant of the universe, and they keep getting different numbers. And so it just illustrates that it's very difficult to solve. So there was a 2014 measurement at 6.67. There was a 2007 measurement at 6.69. So we've, over this 200-year interval, right, what have we done? We've improved our error from 0.1 to 0.01, right? Surprising that we still can't measure the gravitational constant of the universe well. A couple quick notes. Cavendish in this experimental design was actually looking for the density of the Earth, right? He was trying to figure out what the density of the Earth was, which seems a very practical problem. And he actually never mentioned the gravitational constant of the universe. Furthermore, there was actually error in the calculation, so it was actually considerably off, but that was discovered very quickly and fixed. There was actually, some people think the gravitational constant of the universe varies over time. I tend to think, well, maybe, who knows what's going on with the gravitational constant of the universe. Maybe that's dark matter, who knows? And finally, that illustration. The Cavendish experiment is very similar, but that is actually the Cavendish experiment. And here, finally, I'll just show you that we still can't measure the gravitation of the universe, constant of the universe very well. So this is from Wikipedia. So here's 1910. The red lines are sort of literature surveys, sort of estimates based on literature surveys with, you can see, relatively large error bounds. Very little confidence in our measurement of the gravitational constant up until recent times. The blue lines are actually torsion balance measurements, so using essentially the same measurement apparatus as Cavendish, up until, I think that's, 2004, probably something like that. People are still using Cavendish balance measurements to estimate the gravitational constant of the universe. There are some sort of new measurements which are also measuring the same thing, but using different apparatus. And essentially, this is where we think the gravitational constant of the universe is. But I mean, look at this, right? We have a measurement here and a measurement here on either side of that, with error bars which don't overlap, right? So how is that possible? Either the error bars are wrong or something else is going on, right? I don't know, mysterious forces at work. So I think this is optimistic for a measurement of the gravitational constant of the universe. Who knows? Maybe we're going through some gravitational miasma and things change over time, but who knows? So think about the gravitational constant of the universe as accurate, but not that accurate. But again, You don't often use it unless you're trying to measure the mass of a planet. And so hence the gravitational or the motion of binary stars, it becomes an issue there. So again, it's occasionally useful, but we don't use it very much in this class. Again, the motion of the moon and the Earth, it's significant there. Right. So okay, having disposed of that question, the use of mu versus that weird constant, was it g m cubed over m1 plus m2 squared, right? We're going to address another issue with the two-body problem, the model of the two-body problem, which is that it assumes, it's basically an assumption, that the mass of the body is concentrated at a point, an infinitesimally small point. And obviously, the mass of planets are not infinitesimally small unless they suddenly contract into black holes or something like that. And so that's another issue we have to deal with. But I'm going to leave that discussion mostly to the book, right? So Pressing and Conway has a detailed proof that you can ignore the the non-point mass nature of planets, assuming that they're approximately spherical. So I'll just go briefly through the reasoning behind it, how it works. So here's our planet. We want to assume that it's a point mass. It's not a point mass. In fact, there's mass over here on this side of the planet. So if we're measuring our force on mass 2, right? There's part of the planet which is closer to you, right? And so remember that's g m1 m2 over r12 squared. And so this mass will be exerting a stronger force because it's closer to you, and this term is smaller. Likewise, there's a part of the planet which is farther from you, and it's exerting a weaker force. Force weak, force strong. And so, right, these deviate from our point mass approximation. Fortunately, however, they exactly cancel each other out, it turns out. It's not obvious that they do, but they do. The weaker part of this mass exactly cancels out the extra force due to gravity due to the stronger force from this part of the mass. Likewise, there's a part of the mass which is above that point mass approximation, which is actually pulling you a little bit up, right? It's pulling you up. Fortunately, there is a counterbalancing part of the mass of the planet which is pulling you a little bit down. And so those two extra forces, the force up and the force down, are equal and opposite, and so they cancel each other out. And so there's lots of cancellations, and of course you have to establish this rigorously. You have to go through the proof. But I will not do that, just because I've done quite a bit of mathematics in this lecture, and I'm sure you're all tired of it. And so you'll just have to take my word for it, or consult Pressing and Conway for an actual proof that all these deviations all cancel each other out and reduce in the end to as if the planet were a point mass at its center. This assumes a spherical planet, of course, right? A spherical planet. And of course, actually, the Earth is not exactly spherical. It's a little bit fatter than it is tall. It has a little extra mass here. We're going to ignore that until we get to orbital perturbations. I think lecture 11, 10, something like that. So Earth ablateness will become an issue. It actually is a serious issue, but it's not one we're going to talk about right now. Earth ablateness, orbital perturbation due to Earth ablateness. So again, now we've been going through this, resolving all these issues with the two-body problem, which will allow us next class to then come up with reinstating Kepler's 3 laws. So all these slight changes from getting from Newton's universal gravitation back to a derivation of Kepler's three laws. So we first disposed of the two-body problem to the restricted two-body problem, and then we talked about the gravitational constant when the masses are not, one mass is not trivial compared to the other, and finally we talked about the issue of non-spherical nature of the planets. Now, having disposed of all of those caveats and careful analyses and so forth, we can start and solve problems. We're happy with our two-body problem, and we're going to, from now on, just focus on the model where we have negative mu over r, negative mu r over r cubed. Right. So this is our model that we're going to dispose of right now. And of course, this model is mass independent. You don't see the mass of the thing that's moving in this model at all. And of course, that will be very useful because we don't like to develop different equations depending on the mass of your spacecraft. The mass of the spacecraft changes over time as it uses propellant and so forth. And just generally makes life easier to consider mass-free analyses. And so that's what we're going to do. And so starting with this equation, we're going to revisit our invariants from the part A of this lecture, starting with kinetic energy. Right? So in this case, we don't consider the kinetic energy of the planet. We only consider the kinetic energy of the spacecraft or the orbiting body. And we don't consider the mass of that. Remember, technically kinetic energy is 1/2 mv squared. But we're going to drop off the m because, remember, potential energy is also, right, gm m1 over r. And so both of these, we're just going to eliminate mass and talk about this as kinetic energy per unit mass and potential energy per unit mass. So if you're actually interested in the potential energy, I don't know why you would be, the actual potential energy, you would have to multiply it by the mass, but not a serious issue. So we're going to drop off, make these massless, dimensionless. And so we redefine now the kinetic energy in the restricted two-body problem is just 1/2 v squared, makes life easier. And the potential energy, here I forgot my negative sign, in the restricted two-body problem is just mu over r, negative mu over r. And as we've already proven, and this applies here to the restricted two-body problem, the combination of kinetic plus potential energy is conserved. So d dt of that equals 0. And now, having come almost to the end of the lecture, we'll show that actually this property, right, and especially the property that potential energy only varies with your position in the solar system, right, where those, remember, we have r as the distance from the planet, r, and this is v of r only, that can be used to solve some nice problems. I don't actually have the equivalent for angular momentum here, but we will come back to that in the next lecture. It's not as easy to use for solving problems, unfortunately. We'll use it extensively in the next lecture, but we're not using it quite yet. So let's look at a couple problems. The first is where we've got observations. And so we've got some spacecraft cruising around the Earth. I don't know, it's like we observe it here, right? We've got our telescope here. I don't know, there's our telescope. And we observe this object here at a distance, a radius of 20,000 kilometers. Now, it's important to differentiate radius from altitude. Not an altitude of 20,000 kilometers, a radius of 20,000 kilometers. Because all of these numbers are in radius, not altitude. So keep an eye on those homework problems, keep an eye on those problem sets, because if they say altitude, you have to add what? You have to add 6378, right? So r equals altitude plus 6378. Don't forget to add 6378 when necessary. Right. So anyway, our tracking system tracks a spacecraft here at a radius of 20,000 kilometers, and we notice it's moving in some direction. We don't need to know which direction, just some direction, at a velocity of 1,000 kilometers, 1 kilometer per second. Right. So it's a radius of 20,000 kilometers, and it's moving at 1 kilometer per second. We don't know which direction. Not important for this problem. This is enough information to allow us to calculate energy, right? The energy of that spacecraft, which is invariant. It doesn't change with time. So in particular, we just plug in here our formula, 1/2 v squared plus minus mu over r. R is 20,000. V is 1, right? And so we can get the energy of this spacecraft. It's 0.5, right? It's not moving very fast. Kinetic energy is not large, and but its potential energy is well, its magnitude of the potential energy is relatively large, but of course it's negative, right? We're in a well, a gravity well, right? So potential energy is always negative. So we can calculate that number. This is 0.5, and this is approximately 20. 19.93 specifically. So a negative 20, of course. And so we can add 0.5 to negative 20, and we get approximately negative 19.43. So the total energy of the spacecraft is negative. What does that mean? That means it's in orbit. That means it hasn't escaped the gravity well of Earth. So it's whatever happens, it's going to stay in that gravity well. Whatever motion we observe, it's going to always be in that gravity well. It'll never get outside the gravity well and escape to some other planet. Okay. All right, so what was the problem? I didn't define the problem yet. So we initially observed this spacecraft. It allows us to calculate its energy. We later observed the spacecraft a little bit closer to the Earth, at 10,000 kilometers. Right? And the question is, how fast is that spacecraft moving? Maybe it's going to hit the Earth. Who knows? Again, a relatively easy calculation because we know that the energy of the spacecraft hasn't changed over time, unless, of course, it's using thrusters or something like that. But we're assuming it's not. So we've calculated the energy of the spacecraft. It hasn't changed. Our new observation allows us to calculate the new potential energy of the spacecraft. So in particular, negative mu over R2, where this is now 10,000 kilometers. Right? So we have, let's ignore that, we have this number, we have this number, and we want to figure out velocity. Well, velocity is only a function of kinetic energy. Right, remember, t equals 1/2 v squared, and so, of course, v equals 2t square root. And so what we'd like to be able to do is then calculate the kinetic energy at this second observation. And, of course, we can do that because we know this number and we know this number. So we just solve then for T2, right, subtracting the initial energy, this number here, and our new calculation of V2, which is, where it is, it's right here, negative 40. And so we say, well, negative 20 minus negative 40 is approximately positive 20, which is the number we get there. And so then we just plug that number into the kinetic energy and we can get the velocity. So it's approximately the square root of 40, which gives us a velocity of the spacecraft of 6.4 kilometers per second, which is much faster, of course, than we observed it initially, which is only 1 kilometer per second. Now it's moving at 6.4 kilometers per second. So again, you can see this trade-off where we've now sacrificed some potential energy, moved down the well. That potential energy has all been converted to kinetic energy. So all that potential energy now in the form of kinetic energy, causing our spacecraft to move much faster. That's the first problem. Again, right, don't forget there's 6, 3, 7, 8. Don't have to assume anything about the direction of the velocity. Don't have to observe circular orbits or anything like that. Energy can be used for these types of calculations. No, we don't know. No, this is not going to tell us everything about the orbit, right? It's just going to tell us a little information about velocity and position. That's it. We can calculate position and velocity, but we can't calculate direction of that velocity, for example. Right, or absolute position in space. Right, so now finally our last sort of mini thing we can do with energy is to calculate how much kinetic energy we need to escape that gravity well. And there's our gravity well. Here's us on the surface of the Earth. Right, here is potential energy. How much kinetic energy do we need to put into this spacecraft in order for its total energy to be greater than zero, right? Because remember, if its total energy is greater than zero, it will be able to convert all that kinetic energy into potential energy and sort of pay the piper, right? It'll be able to pay this toll required to get out of the gravity well of the planet. All right. So, how do we calculate this? It's, again, right, relatively easy. We have, first of all, the potential energy of the spacecraft at the surface of the Earth, and a desired total energy once we've left, which is 0 or greater than 0. So our desired energy is 0, or it could be greater than 0, but we're just going to make it 0 for the point of discussion. And so that is, of course, a combination of kinetic plus potential. And we know we're on the surface of the Earth what the potential energy is of the surface of the Earth. It's mu, negative mu, over our Earth, which is, of course, 6,378. And so, right, we can calculate this number. We know this number, and so all that remains is to calculate this number and then use it to solve for velocity, because remember, velocity equals square root of 2t. Right. So, okay, so how do we do this? So, for example, actually, in this problem, I'm assuming we're not at the surface of the Earth, but so I thought we were going to do that. Oh, sorry. Yeah, in this question, right, we have initial position of 20,000 kilometers. Okay, so let's work with 20,000 kilometers here. So it's not the radius of the Earth, 20,000 kilometers. If you wanted to calculate the escape velocity from the surface of the Earth, you'd do 6,378. But I guess I already calculated the number for 20,000 kilometers, so that's why I'm using it. I don't know. In any case, we know the potential energy. We can figure it out based on negative mu over r in this case being 20k, 20,000 kilometers. And we'd calculated on the previous slide, that's negative 20. Right, so this number is negative 20. And so we can easily calculate then the required kinetic energy for our total energy to be 0, which is T equals negative V, which in this case is positive 20, because V is negative 20. So that gives us a desired kinetic energy of greater than 20. And so we can just plug that into our desired velocity, square root of 2t, which is 40. And that gives us an escape velocity at that radius of 6.313, which, if you remember, is sort of the same number we had on the previous slide. But in any case, that means that at a radius of 20,000 kilometers from the center of the Earth, if you have a velocity of 6.3 kilometers per second, you will deorbit the Earth, right? You'll escape the gravity well of the Earth because you have a sufficient amount of energy, total energy. Your total energy is net positive. It means you're no longer in an elliptic orbit around the Earth. Kepler's 3 laws don't apply to this case, and so you're going to escape and go off to another planet or fall into the surface of the sun or something like that. Notice we don't need to know what direction this velocity is. It could be any any direction. Again, we don't have that kind of information yet because we only have this one invariant that we're working with, which is energy. But the magnitude of the but the magnitude is enough to calculate some interesting things. Maybe not everything that we're interested in, but some interesting things. And of course, next lecture we will be talking about the rest. Right? We have to bring angular momentum back into the picture, and we'll use that angular momentum to then define the geometric invariance of orbital motion. In particular, we're going to consider planar motion initially, and so we're just going to be considering magnitude of angular momentum in the next lecture. So again, next lecture we're going to be talking about derivation of Kepler's 3 laws, really, starting with this first law. Specifically, we'll talk about the eccentricity vector, how to calculate orbits, how to get the eccentricity in the semi-major axis. And then we'll use that actually to calculate the other 2 laws of Kepler's motion. And finally, then, in following lectures, we'll extend this to non-planar motion, so the 3-dimensional motion as well. But then again, that is another lecture, and I just don't want to get ahead of myself. And I'm sure you are ready for a break. So now is the time to stop recording. See you next time.